of the integral x from 0 to x of the root of t squared plus 4 dt. Okay. Now, the first step that we do is that we take is that we have to define our function. Okay. So let's say let f of x. Okay. Should we? Okay. Let f of x. Yeah, no, so let f of x be equal to let's say the root of x squared plus 4. Okay. These are f of x. Okay. Now let's take note of this. If you did statistics, okay, you come across something like the integral of the small f is equal to the big F. The same way the differential of the big F, okay, gives you the small f. So something like this, okay. So now we can make our substitution, okay, and we get the differential with respect to x of the integral of f of x. Okay. Now the fundamental term is a question like is a concept that I think will come in the exam because when I went through the problem set, I saw most questions like coming from the fundamental term. That's why I'm going through this again. Okay. So now with this, right, let's solve this part first. Then we proceed. Please, if along the line there's a part that is not clear or I'm confused, you kindly let me know, okay, before we proceed. So this part, okay, we can make the substitution and we get the x of, and remember the relation we did, okay, the integral of small f gives us a bigger f. Now these two are just functions, so f of x is just a function. So yesterday we saw that if f is equal to let's say x plus 1, okay, f would be equal to x squared plus 1. Okay, so they are both just functions. Okay, it's very important we know that. So this integral gives us what? The bigger f. Okay, and we are still integrating on the interval. Okay, so from 0 to x. Okay, now remember that f, small f and big f are both functions. Okay, now let's look at something. So we have ddx of um the square bracket f of x, okay, minus f of 0. Okay, now if you have a function, okay, and you plot in a constant, okay, like a certain number, you always get a number. And we saw that if you differentiate a number, right, so this f is a function, okay, and you are plotting in 0, so we'll always get a number. Do we see it? So if we differentiate that number, because remember that this thing we are seeing here is equal to what? D dx of f of x, right? Minus d dx of f of 0. Okay. Now, what we are saying is that you are putting the constant in your equation, right? So you get a certain constant. So, for example, if x were to be, if f was x squared plus 1, okay, and you are putting in 0, okay, you end up getting what? And 1. Okay. Now, if you differentiate your constants, you always get 0. Like any, so your so if you put in, so in this case we had 1, okay. If you change the function, you get like a number, you always get a number. If you differentiate that number, you always get 0. Okay, because the differential of a number is 0. So we'll always get a 0 here. And of course, we'll get the differential of f of x. Now take note of this. We said that the differential of the big F gives us small f. So this gives us what? Our capital F back. Now, let me say this, okay? The calculus now is more of steps than your final answer. Okay, so as we've been doing for the recent times, okay, the steps that you follow through is very, very, very important. Now, let me go like over this again. I said if for this question, for instance, right, they are telling you that x is greater than 0 in the question. If you start solving it, you have to state this because this will be worth 1 mark. Okay, you have to redefine once you rewrite the question and you don't write the interval in which it is defined, then you've made a big error. Okay, now just to solve this, okay, we literally went through the fundamental theorem again. Okay, so like every step, try and write. It's not like always that you have to write in math terms. If it's a sentence, just write it. I'm doing this because of that, like something nice. Okay. So now let's take note of this. Wait, let me check if there are questions in the chat or there's somebody in the lobby. Okay, so there's no questions. Okay. So now we've seen how we've seen how when we differentiate, right? No matter the constant here, since we are putting in a constant in the equation, right? We will always get 0 because we are differentiating a constant. Okay, so hope this is clear. So I'm going to clear my board, then just a second, please. Okay, sorry for that. Let me clear this quickly, then we proceed. So we have so we got f of x, right? So we got f of x. So our final answer. So this was the original question. We were asked to find the differential of the integral from 0 to x of the square root of t squared plus 4 dt. Okay, and when we solved it using the fundamental theorem of calculus, we got f of x, right? So now we can conclude that, and you remember that we defined f of t earlier, right, as this part of the function. Okay, so we said it before we began that f of t is equal to what, the square root of what, t squared plus 4, right? This of what we had, and when we solved this, we had f of x. So we can say that then f of x is equal to what, the square root of x squared plus 4, and this becomes our final answer. Okay, so please, what we did, is it clear? Or so I'll just give one more example, then we solve the question. That so now we are just doing a recap of what we did yesterday. Let me clear this quickly. Yeah. So now the question that we solved, right? We saw that the x was at the top. Okay, the x was at the top. So what if the x was rather down? So what if we have something like this? So okay, let me use the same question. Okay, but now let's solve for x being beneath. Okay, now if x is beneath, okay, so let me write the question again. T squared plus 4 dt. Now for the questions, okay, you will not be told that use fundamental theorem of calculus. Like they can tell you, but often they will just tell you that solve the differential. So if you see this, it's up to you to see that you can use the fundamental theorem of calculus to solve it. Okay, now let's see. Okay, so now we swapped our x and our y. Okay, let's use the same steps that we used before. Okay, now let f of t, okay, be equal to the inner function, the square root of t squared plus 4 t. Yeah, so let f of t be this. Okay, now we can redefine our function as the integral from x to 0, okay, of f of t. Okay, so now we are finding the differential of the integral. Okay, so we have to bring this. Now we saw that the integral of f, okay, now this gives us what dx of capital F dt. Okay, still over the same interval. Okay, so let me admit. So we are still defining the function on the same interval. Okay, now we saw that. So let's just separate our differential from our integral. Okay, and let's solve the integral first. Okay, so now of f at 0, okay, minus f at x. Now we saw that if you put in a constant in a function, okay, you always get a number. So in the previous example that we did, we saw that if you have f, right, small f to be equal to x plus 1, okay, the big f of x would be what? X squared plus x. Do we see it? So no matter the type of function that you have, the fact that you are putting in a number, okay, you always get a number. We are putting in, we can rewrite this as d dx of f of 0, okay, minus d dx of f of x. Now, differentiating a constant, you always get 0. Now, this is the part that I want you to take note of. So, if you get 0 here, right, you will get negative d dx of f of x. Do we get it? Now, we saw that if you integrate small f, okay, your small function, and you get your bigger function. If you differentiate your bigger function, right? Oh, let me admit to this person. This is doing that. Okay. If you differentiate the bigger function, right, you end up getting the smaller function back. Okay, it's just the reverse. Okay. So now this gives us what? F of x. Sorry, negative f of x. So all I'm saying is that when x is down, okay, you always get a negation of your answer. Okay, and there's one law in derivative that let's see, the integral from a to b, okay, of f of x is equal to the negative integral, right, of b to a of f of x. That's the same thing that we have here. Okay, it's the same concept that the fundamental theorem of calculus is also applying. Okay, so if you swap, so if the x is now beneath, please kindly take notes, okay, because these are the tricks that are often in the like in the questions like that we are often examined on. Now let's take a look at one example that is in the exercises that was sent by the lecturer. Now, if you are new here, okay, the lecturer sent some exercises, okay. So we are going through them like step by step, okay. So now let me write the question, then we see how we solve. Okay. Okay, so now we have let y be equal to. I want my presentation to be stylish today, so I'll be switching colors a lot. Pardon me for that. So we have from 0 to tan x, okay, of the square root of t plus the root of t, the t. Okay, so this is the question we have. This was the question in the slide, okay. Now, yes. So now, from observation, okay, we don't have just x here, okay, but we have tan x, okay. Now, let's please take notes of this, okay. Now, we are going to use the same concepts that we've done, okay. So the question states that find the derivative of the following functions, okay. And this was one of the function. It's up to us to know that, okay. So they are asking me to find the derivative using the FTP because I have an integral. So if I have to find the derivative of the integral, then I have to use FTP, okay. Now we are using the same thing. So let f of x, okay, let f of t, okay, be equal to the square root of t plus the root of t. Okay, so we can make the substitution. Y is equal to the integral of tan x to 0, right? Of f of t. Please hope that's clear. Please, if there's like any question, kindly like drop it in the chat or like unmute and speak. Okay, is very important to me. Okay. So we have this, okay. We have this. Remember, we are finding the differential, okay. Finding differential. Now we can solve for the inner part first. So let's try and simplify this, okay. Then we solve for the outer part. So y is equal to d. Sorry. So dy dx, okay, is equal to d dx, okay, of f of t, okay, on the same interval, okay, from 0 to tan x. Sorry, I have to admit someone in because I think the network is bad, so I always have to pause to do that. Apologies for that. Okay, so we have this a relation, okay, and we saw that we can break this down further, okay. So we have dy dx, okay, because we are finding the differential, okay, of d dx, okay. Now let's put this in a bracket, and we have f of, now we are replacing the inner part with the tan x and the 0. So if you have something like f is equal to what, x squared plus 1, okay. Now if you are finding the integral of f, right, of f of x, okay, the integral of f of x over 1 to 2, 1 to 2, okay, we get x cubed, right, on 3 plus x, okay, and we define this from 1 to 2. So we just put in the 2, okay, then we subtract the 1 from it. So we get 2 to the power 3 on 3 plus 2, okay, minus all this minus, right, minus 1 on 3 plus 1, okay. This is what we are doing, okay. That's the same thing we are doing here, but just that in the case we are doing, in the case of the example we are doing, we are using tan x and 0 instead of the 2 and the 1, okay. And of course, instead of the x, we have t. Okay, so now instead of the t here, we put in tan x. Okay, minus, sorry, this looking too messed up. Let me try and rewrite it. So we put in tan x, okay, minus the f of 0. Okay, now we can separate this differential, okay, but I'm not going to do that because of space. So we get dy dx is equal to, now take note of this. We are going to use the chain rule. Okay, now what does the chain rule say? Okay, so if we have, tan, let's say tan, no, let me use a similar example so that it becomes clearer. So let's say we have oh no, so we have tan, okay, tan x, okay, and everything to the power 5. Okay, now what the chain rule is telling us is that, so let me write the formula, try and write the formula for the chain rule. No, I don't think I remember. So let's use this example, okay. So we differentiate the outer part and we come to the inner part, okay. So we have a mod this to the power 5, okay. This is similar to x to the power 5. Now, how do we solve this? We just differentiate, like we just bring the 5 here, okay, and subtract the power by 1, okay. Now, that's what we've done. Like, that's the same thing that the chain rule is saying. But just that after we have to differentiate what's inside. So now let x be r tan x, okay. So we have to differentiate the tan x and multiply by this, okay. So we have 5 times tan x to the power 4 times sec square x. Okay, so that's a similar thing we are coming to do here, okay. But in this case, right, uh x to the power 5 is our f. Okay, we don't know what that is. So our differential becomes f prime, okay, the differential of the outer part, okay. Then what does the chain rule say? We just bring in the inner part unchanged times what, the differential of the inner part. Okay, this gives us what, sec squared x. Okay, now remember what you said earlier, that f, that small f and capital F are both functions. So if you put in a value inside and you differentiate, right, you always get 0. So this gives us 0, right? Minus 0. Do we see it? Now we saw that the differential, so we integrated small f to get big F here, right? We integrated small f to get big F. Therefore, when we differentiate the big F, we get our small f back. So this gives us what, dy dx. Let me use um a different tone. Okay. So we get dy dx, okay, is equal to what, small f tan x times sec squared x. Do we see it? Now our f is what? Our f is this thing. Okay, is this thing over here. So all we have to do is to make the substitution. Okay, so we get now our t's are tan x. Okay, so we get the square root of tan x. Okay, plus the root of tan x. Okay, times sec squared x. This becomes our final answer. Please hope you all get what we just did. Hope you all get what we just did, please. Let me check if there's a message in the chat. Hope what we just did is clear. A thumbs up or something, like I want to get confirmation before we proceed. Please, is what we did clear? Hello, hello, is it clear? Wait, can you hear me? Okay, okay. I have one confirmation. Like, can I get one more, please? I want to be sure. But if you don't get me, kindly let me know. Okay, kindly please let me know. Okay. So we are continuing. Okay, so let's look at the next question that we did. Now I've sent a question. How should I put it? Sorry, what is it even called? A paper? Is it paper? A picture to the group. Okay, and it has a certain relation. Okay, it has a certain relation. Let me try and write it down. Let me try and get that and write it down right now so we can take. So this actually, like calculus 1 is like they are, I'm assuming that you've done calculus 1 like and every part of it. So some concepts like you need the concepts from calculus 1 to like solve them, you see. So this was what I put in the group. Okay. And you see that it's the same thing that the fundamental theorem of calculus is also I'm applying. Okay. Now now we have, if we integrate right from a to a, okay, of f of x dx, you get 0. You see it. And the second formula that is also on the this one is that we have the integral from a to b, sorry, of f of x dx. Okay, is equal to the negative integral, okay, from a to b of f of x dx. Okay, and the last one is that the integral of b to a, okay, of f of x is equal to the integral of c to a of f of x plus b to a of f of x dx. Okay, this is what we have. Now take note of something. This one here, this one here is what we saw in the fundamental theorem of calculus. Okay, and we saw that when you solve the x, okay, you have to bring in a negative. And so why there will be a negative with respect to the FTP. Okay. Now with this also sometimes there is a discontinuity with this one. Okay. There is a discontinuity at C. Okay. So you just, oh sorry, there's a mistake here. Here is supposed to be C. Yeah, C. So to C. So it's like we are moving from A to B. Okay. But we can't have C. Okay. So what we can do is that we find this part. Okay. Then we come and take the second part. Okay. Now the smaller one is always down there. So A is smaller than B. Okay. So now in this case, we move from A to C. So we move from the smallest one to the medium. Okay. So from A to C. Okay. Now B is the biggest. So like from B to C. Okay. Like that's why we have this formula. Okay. Now I would like us to take a look at this formula. And this formula was we were actually examining on, like we were examining on this formula. Okay. Like this one is very, very, very important. Let me clear this space so that we just see the example we would be doing. So today I would like to take my time because I want us to all understand what we are doing. And tomorrow we'll have a final section. Okay. So our final section tomorrow, we'll be looking at series. Okay, the series and the sequence. Okay. I'll try and get as many questions as possible so that we can like just go through many of them. Yesterday we saw the P series. We also saw the geometric series. Okay. So let's take, so let me write the formula again so that we can look on and solve. We have the integral from a to a of f of x is dx is equal to a. Okay. Now, so let me just use an example for this so that we just move on. Okay. So let's see f of x, right, is equal to x squared plus 1. Okay. Today is like I'm sticking to x squared plus 1. Okay. Now, let's find the integral, let's say from 2 to 2, okay, of x squared plus 1. Okay, of x squared plus 1. Okay, so the integral gives us x cubed on 3 plus x. Okay, from 2 to 2. Okay, now this gives us what? 2 cubed, okay, on 3 plus 2, and all this minus 2 cubed on 3 plus 2. Okay, so let me make so this and this cancel out, this and this cancel out, giving us a 0. Okay, now let's look at this question that we solved yesterday, and there was a mistake in the solution I did. Okay. Because yesterday's section was live, so I didn't have to like sorry. Sorry for that. So there was a mistake. So I went back and saw that I did a mistake. Okay. And if you wrote the solution from yesterday, you said that we had okay. So let me write the question first before I even start talking about it. So we had a question like this, and I'm sure most of us have seen it before. It's probably also a past question, so um, it's important we go through it. Okay, so we have eight. No, let me not use. Let me use. So we have eight. Okay, now eight plus the integral from x to c. Oh, sorry, from c to x. Okay, the smaller to the bigger one of t squared. Okay, of f of t dt, and this is equal to 4 root x. Okay. Now the question was that find your c. Okay. Now that's what the question is saying. Like find your c. Now how can you can't find c when you have a let me say a differential? Okay. So we have to get rid of the differential and try and do something like we don't know the particular step we have to do, but we know that we have to get rid of the differential. Okay. Now differentiating this, the 8 goes away. Okay. So we get 0 plus what? Now, in this case, we are applying the FTP, okay, the fundamental theorem of calculus. Do we see it? So, applying the fundamental theorem of calculus, we can see that we have just x here, okay, and we have a constant, okay. So let's, should I solve this? No, I'll solve it step by step, okay. So, just a second, please. So, let's continue. Sorry for the delay. Sorry, apologies. Yeah, so we differentiated 8, okay, and we had 0. Okay. Now with this, we are going to apply the fundamental theorem of calculus, and we can see that um depending on the marks that is allocated for the question, if like this question were to be 5 marks, okay, then you can conclude that by the fundamental theorem of calculus, right? The differential of this gives us what? Just so let's solve this step by step. Okay, let's solve this step by step. I'm trying to find a way to dump it back. No, let's solve this step by step. Let me go back. So we have 0, okay. And from the fundamental theorem, right, we can just put in our x, okay, because we have just x, okay. So even if you are using chain rule, you have f of x, okay. We have f of x times the differential of the inner part, okay. Now the inner part is x, so times 1, okay. So as we saw from the FTP, we can just write this function, right, and just swap with respect to x, okay. So by the FTP, the differential of this, right, will give us what? X squared f of x, okay. And this is equal to the differential of this. So we can just factor out our 4 differentiate root of x. So the differential of root of x gives us what? Let's see. So we get let me see. So we get yes. So we get x to the power negative 1. Okay. Negative 1 and 2. Okay. I'm coming. Why? Why? So x. Okay. Yeah. I was just overthinking this. So we have x to the power negative 1 on 2. Okay. Times 1 on 2. Okay. So we can cancel this out and we get 2. So we get x squared, right? F of x. And this is equal to 2 the root of x. Okay. Now f of x is equal to what? 2 the root of x to the power half, right? Times x to the power negative 2. So we end up getting f of x is equal to 2 x to the power negative 5 on 2. Okay. Now we have f of x. Okay. Now remember the question. We have been asked to find c. Okay. Now we have found our f of x. Okay. So let's put our f of x back into the original question. Okay. So we have 8 plus the integral from c to x, right? Of t squared. Okay. Now here we have f of x, but in this case we have f of t. Okay. So we have times 2t to the power negative 5 on 2. Okay. And this is equal to 4 the root of x. Now please take note of this. Okay. Like let's take note of this. Now we are integrating, right, from a random number c. Okay. Sorry, from a particular number c, okay, to a variable x. So c can be like let's say 2 to x. Okay. Now from this, okay, we can just pick this part out. Like we can just pick this part out. Okay, please take note of what you are doing and say that okay, let c be equal to x. Okay, let the value you don't know be the value you know. Okay, and c you don't know c, but like you are having two variables. C is just representing a definite unknown variable. Okay, so when c is equal to x, we get what the integral from c to c, okay, of t squared, okay, times 2 times t to the power negative 5 on 2. Yeah, we can simplify this. Okay, so when we do that, we get from c to c of, we can bring out r2, okay, of t to the power negative half. Now we saw that if we integrate from a to a, okay, over the same intervals, right, we get 0. So we can say that this is equal to 0. Okay, so we can solve this. Okay, what's the integral of this? Okay, we get t to the power half. Okay, and we have on 1 on 2. The 1 on 2 just comes to the top, and we get 4. Okay. Okay, so sorry, let's continue. Where were we? Okay, okay. So we get 4 still from c to c. Okay, this gives us 0. So when we do this, we still see that once we say let C be like equal to um be to X or something, right? We can see that this part, okay, when C is equal to X, okay, when C is equal to X, okay, when C is equal to X, okay. So we can see that this entire part, okay, gives us 0, okay. So what we were doing here is showing that when we do this, we get 0, and from this is clear, okay, when we solve this, you get 0 is equal to 0, and that one is not defined. So we can just conclude that I'm integrating from C to C, okay, gives you 0, like something that simple, okay. So if you wanted to use the routes that we use, you don't have to bring the is equal to 0, okay. You just have to solve this. You get 4 multiplying the bracket, the root of um c to the power half minus c to the power half, and they just cancel out, and you get 0, okay. Then you put the 0 back into your original question, because we are saying let c be equal to x, okay. Hope you get what you are doing, please. So if x is equal to c, right, this entire part goes to 0, okay. And we can have 8 is plus 0 is equal to what? 4 root c, okay. So 8 is equal to 4 the root of c, and we get the root of c is equal to what? um the root of c is equal to what? Let's see, 2. So we can just square both sides, and we get c is equal to 4, okay. So that's just the solution that we had to do. So what we did here was that you just take c to be equal to x, okay. Then you conclude that since you are integrating on the same intervals, okay, you will get 0, okay. Then you just find your c, okay. So that's how to solve this question. Please, hope you all get what we just did, or should I go over? Hope you all get what we did. This was one of the questions we did yesterday, and I had to redo it and come back, okay. So thank you very much. Um so we can say that with this question, okay, we are again applying the fundamental theorem of calculus, okay. So if you don't know the fundamental theorems, there are two, okay. What we did was the first one, okay. There's one second one there also. You can kindly look at that. So now we are going to solve one more question, okay, and we are going to be using some concepts that we learned, okay. So let's see. I think I have two more. Yeah, let's see. Okay. So let's solve this question. Okay. So with this question, I would like us all to try it, okay, in the next, like, let's say 10 minutes, okay. No, 10 minutes is too much. 8 minutes, okay. Then after we solve it together, okay. So I'm writing a question. The limit as t goes to infinity of the square root, sorry, of the integral of, no, okay, come. Let me get the exact questions from the PDF, so I can, just a minute, please. Okay. So the question is evaluate the integral. Okay. Evaluate the integral. Evaluate the integral. Oh, my handwriting is so horrible. And let's see. So we are doing question 4C. Okay, question 4C. So evaluate the integral from 2 to infinity of 1 on the root of a, sorry, it's not reading. 1 on x minus 1 all squared dx. Okay, so this is the question we are doing. Let's all try and solve at 6-5. Okay, we come together and see the answers that we have. Okay, so please let's all try and solve this question. Okay, let's all try and solve this question. Yeah. Okay. Okay. So please please did somebody try it? Which answers did we get, please? Did somebody try it? Hello. So now with this question, we can see that we are being asked to integrate to infinity. Okay. And infinity, of course, is a very large number. So we can't. Sorry, can you hear me? My network was out for some time. So can you please hear me? Hello, can you hear me? Okay, thank you very much. So we can't integrate, okay, um from infinity because we don't know infinity. Infinity is a big number. Okay, so that's so what we can do is that we can we can replace the infinity with a variable, okay, and find the so what okay so let me explain this way. The concept of integration, okay, is that having a box, okay, it's like it's dividing the boxes into smaller parts and bringing them together. Okay, so that's what the concept of integration is about. So if you are having something like this, it's like you are finding the area, okay, the area from 2 to infinity. So what we can do is that we can use the concept of limit. Okay, so we can redefine this as the integral from 2 to t. Okay, as t approaches infinity, the limit as t, right, approaches infinity of the same expression. Okay, let's call this a function. Okay, so now we can solve the limit, and after we solve the limit, we can conclude that that's the final answer, since we can't solve the integral at infinity. Okay, so now let's solve the integral. So we have the limit, okay, as t approaches infinity, okay, of the integral from t. Yeah, hello, hello,
Please, your screen is not
hello.
on. Yeah, please, your
My
screen
screen is not showing.
not sharing. Yeah, it's not sharing.
I can't hear you, please. You said my screen is not showing. Please can't you
Yes,
see my
please,
screen
your
so that
screen is.
I just okay. Please, is it there like only one or we all can see my screen? Hello, it is showing. Oh, okay. Then I think that you should like refresh or something. No? Okay, bro. So please kindly refresh and join us back. Okay. Yeah, maybe the network. Okay, so we can find the integral. Okay. So we have okay, so let's just write this. So this is the same as what the limit as t approaches infinity of the integral from 2 to t of okay. It's simpler this way. So we have what we have. Let me admit him. Okay, okay, okay. So we get so solving this integral, okay, we get -1, okay, on x minus 1. Okay, so this is what we get. Oh, sorry. This shouldn't be there after you solve your integral. Okay. Yeah, that part shouldn't be there after you solve your integral. So now we are just solving the limit. Let's go over this again. I've made a mistake. Let's go over this again. Okay. So the limit as t approaches infinity. Okay. of -1 on x minus 1. Okay, this is your integral, and we are defining this over 2 to t. Okay, so making the substitution, right, we have the limit as t approaches infinity of what? -1 on t minus 1. Okay, this minus -1 on 2 minus 1. Okay, so now we get, oh, so now we get what? The limit as t approaches infinity of -1 on t minus 1. Okay, and this gives us, let's see, plus 1. Okay, because we get -1 on 1. Okay, so we get plus 1. Okay, so this is equal to what? The limit as t approaches infinity of t, okay, t minus 2, okay, on t minus 1. Okay, so you can simplify this and confirm the answer. So what you are doing now is just solving the limits. Okay, so we can multiply both the top and the down by 1 on t. Okay, and we end up getting, let me change my color, we end up getting what? 1 minus 2 on t. Okay, this on 1 minus 1 on t. Okay, and remember the limit as t approaches infinity. Okay, so this gives us what? 1 as our final answer. Okay, so all we just did was that if you are asked to find a limit over infinity, okay, you can represent this such that you find the integral, you find the limit as t approaches infinity. Okay, but like as t gets close to it, because we can't find at infinity. Okay, so like this is just the concept behind it. So now the next thing that I would like us to look at is convergence of positive term series. Okay, because there's one example that I would like us to solve. The last question in the last question of question 4 in the slide, sorry, in the questions that we were asked to do. Let me try and write the question down. Okay, just a minute, please. Try and get that question. So the question is that find the radius and interval of convergence, okay, of this. Okay, so this is the fourth question in the questions that we are yet to do, but we won't be solving this today. Okay, so for the questions that we are yet to solve, I'm being selective. Okay, because most of them we've done them in the previous classes, and the ones that I think we have to go through them are the ones that we are going through them. Okay, so if you have the questions that were sent, now you can see that the question 6, okay, one was in the IE and one was also in the exam. Now, last year, right, the IE questions are what came inside the exam, like I think about 50%. Okay, so let's kindly go through them. I've sent the questions and solutions. Okay, so you can just go through them, and please watch how the answers were presented. That's what saved the marks. For example, as I like always say, the intervals, like you, when you are given a question defined on a particular interval, you have to bring the interval. If you are using like MVT and the rest, you have to state them before you start, because MVT is just the formula, but they are checking if you know the conditions that the law or the formula is defined. Okay. Now, the thing that I would like us to look at before we look at this tomorrow. Okay. So tomorrow, maybe just 1 hour section. We'll just be looking at this, the last section of the series. Okay, then we are done. So what we'll be looking at right now is positive term series. Okay, convergence of positive term series. Now I'd like you to take note of this very, very, very well. Okay, I always say this, like last time I solved that concept in an exam. I told myself that I'm not going to make that mistake, but I came back and realized that I forgot. Okay, so this what. So now let's see convergence. Okay, convergence of positive term series. Now there are three. Okay, there are three types of this series. Okay, let me use red so that now the first one is the integral test. The second is the P series. The third is the comparison. And the fourth is the limit comparison. Now, when you are given this kind of questions, okay, it will be hard, like it will be hard that even if you don't know, you get zero. Why? Now, this all fall under positive term series. So if you're asked to determine whether, like, how should I put this? Or to determine whether it converges or not, like those kind of things, like if the series converges or not. Okay, it's actually quite simple. Okay, now this why I'm saying it's simple. Okay, so let me give one example, then we use the example to solve it. Okay, okay, so let's okay, so let's start with the integral test. Okay, so let's start with the integral test. Yeah, let's take a question on the integral test. I'm trying to guess a question that will make sense. Okay. Okay, so now show that this series converges, okay, by the integral test. Okay, so we are starting them one by one. Okay, or let me take the question that was given to us in the exam. Okay, so let me try and get just 1 minute. Okay, so that we just solve it, so we don't have to do that again. Just 1 minute. Okay, now the question was that use the integral test. So the question was telling us the test to use to determine if the following series is convergence or divergence. And the series that was given is the integral when n is equal to 1, okay, of 5 on n plus 1. This was the question that was given. Now take a look at something. As I said, these three types of tests, okay, fall under positive term series. Now for positive term series, okay, one, they have to be continuous. Okay, they have to be two, they have to be decreasing. And three, of course, they have to be positive. Now, somebody will ask that, how can I show that it's continuous? Okay, you don't have to show that it's continuous. Every question you just okay. So let me solve this. How I will solve it in the exam. Okay. So the only one of these three that you show, okay, is the decreasing one. That's the only one that you show. So if you are solving this, okay, so let's start solving the decreasing first. As I said, you can't solve you can't okay, you can't differentiate with respect to n. Okay, now these questions, okay, these series are defined on a set of integers. Like usually, okay. Oh, let me admit this person. Okay, on a set of integers, okay, and we know that differentiation integration, okay, works on real numbers, okay, real numbers. So we have to redefine this as f of x is equal to 5 on x plus 1. Okay, so let f of x be equal to this. Okay, now to show that it is decreasing, there are two ways. Okay, the first thing we can do is that we have to find a differential. Okay, and that's what I like. But sometimes you can't find a differential, so you have to use the second way that we would be looking at. So f prime of x is equal to what we have. So I'll be solving this first. Okay, we have x plus 1. Okay, times 0 minus 5. Okay, and 5 times 1 on x plus 1, okay, all squared. So we end up getting f prime of x to be equal to what? Negative 5 on x plus 1. Now, by observation, we can see that no matter the value of x that you put in this function, okay, you always end up getting a negative value. Okay. Okay. So because it is how should I say it? Because it is the differential is negative. Okay, we can say that, okay, since we have a negative differential, right, f prime of x, okay, is decreasing. Okay, it doesn't mean it's no longer positive. If you get a negative value, it means that you satisfy the conclusion of the function, like of the expression, like of the series, okay, being decreasing something. Okay, now we've done the decreasing part. Now you can, for the positive, you can say that by observation the function is always positive, because you can see that, not function, sorry, the series, because you can see that no matter the number that you put inside, okay, you always get something positive. Okay, because um okay, so this was defined on the interval, right? X is greater than 1. Okay, because if x isn't greater, sorry, n is greater than 1, okay, this was in the question, and you stating this before you start, it's actually 1 mark, as I said. So by observation, this is decreasing. Now we haven't like even began showing finding, like solving for the question that we were asked. Okay, now what was the question? The question was that eh, the question was that, show that you using the integral test, right, the following series is convergent or divergent. And as I'm saying, since the integral test, right, is one of these three, okay, then it falls under the convergence of positive term series. Now for negative, therefore is decreasing. It's positive. How is it positive? By observation over this interval, so that no matter the value that we put in, we'll always get a positive something. Now, they will not give you a question that doesn't satisfy this theory. Okay, but they want to see whether you know that this has to be satisfied before you begin solving. Now, for the question that, okay, what you've given us is continuous. Okay, then you start solving. So okay. So the questions that I sent you, right, just what we just did. Okay, what we just did was what, let me see, was what, 5 marks. Yeah, 5 marks. I remember very well, 5 marks. Yes, this alone, and finding that is decreasing is worth 3 marks. Continuous is 1, and positive is also 1. Please hope you all get what we just did. Okay. Now to find that it is decreasing, we integrate. Okay, because we are using the, sorry, to find whether it converges, we use the integral test. Okay, so for the integral test, we integrate. Okay, from a to infinity of f of x dx. Now in this case, right, we are integrating from 1 because the series is defined from 1. So we have this is equal to the integral from 1 to infinity of 5 on x, okay, plus 1. Now, you have to be careful here because as you can see, okay, as you can see, I'm no longer using the n to find the integral. Okay, so if you have a series, okay, and you are finding the limit and you want to use L'Hopital, you have to change your n to x because L'Hopital is not defined on integers, it's defined on real numbers. The same way, if you are doing integration, right, or differentiation, you have to redefine your series, okay, because we are defining it over a set of real digits, not integers. Okay, so something like this. Now, to find the integral of this, of course, we can just bring the 5 out and solve it. Okay, so we get something like, let's see, let's try and do this together. So please kindly take note of these three: the integral test, the P series, the comparison, and the limits comparison. Okay, and we say that before you solve any of these three tests, you have to show that it is continuous, it is decreasing. Okay, now we must solve this, okay. But when you show that its degrees is converging or diverging, you concluding also, like your conclusion, okay. What's the conclusion? You can say that um since this does this, then this is divergent. Doing that thing alone is worth 2 marks. So your answer is worth 7 marks, and your presentation, okay, is worth 8 marks. So that's what I'm talking about. So let me clear this, okay, and let's continue with the solution. Let me quickly clear this. So after then we take one more example, okay, then we can call it a day. So let's see. So we had the sorry, we had the uh, the integral from infinity, okay, to 1, okay, of f of x dx, and we saw that this was equal to what? The integral from infinity to 1 of f of x, and our f of x was what? um 5 on x plus 1 dx. Now the same concept is here again. We can't integrate over infinity, so what can we do? We can use limit, okay. So the limit as t, okay, approaches infinity, okay, of from 1 to t of f of x. Now f of x is what? 5 on x plus 1, okay. Remember why we are not using n anymore, okay. So now you solve this integral, okay, and you get the limit as t approaches infinity, okay, of, let's see, what do we get? 5, okay, multiplying, sorry, trying to do this. So we can bring out the 5 here, okay, and we know that the integral of x plus 1, okay, is equal to the natural log of x plus 1. Okay, hope that's clear. So let's quickly do this. It's equal to the natural log of x plus 1, okay, still on the interval t to 1, okay. So we get 5, okay, the limit as t approaches infinity of the limit, sorry, of the natural log, okay, t plus 1 minus the natural log of 1. Please, do we see it? Okay. Now, remember we have the 5 here multiplying everything. Sorry, we have 1 plus 1. Yeah, so this is supposed to be 2. Okay, yeah, this because we put in 1 here also. Yeah. So we can see that if you put in infinity, okay, this will give you like infinity. And sometimes it's safer if you don't write things like 0 times infinity or something, because some of them are not correct. So from this, you can conclude that this is equal to what? Infinity. And since you didn't get a particular number that this um integral test, this series converges to, okay, you can conclude that since the integral diverges, okay, then by the integral test, okay, the series, okay, 5 on n plus 1 diverges. Okay, so when you state this again, then you get what? 2 marks. So not just in this question, but like your conclusion is also very important. So let's take one more example, okay, on the convergence of positive prime series. So let me see the example I should do. Which example should I do? Okay. So let me see. I have one example. I want to see it. Okay, so we've done integral test. So let me try and pick one that involves multiple, so we can just solve them together. I'm looking for a particular example, but it seems I can't find it. A particular one that involves us using like multiple of these proofs. Okay, so let me just pick one. Let me just pick one. Okay, so we've done integral. So let's pick the P series. Okay, let's pick the P series. Okay, so let's determine whether or not this converges. Okay, let's see. Let's sum to infinity, starting from 1, 7, and plus 3. Okay, so let's determine whether this. No, this is geometric. Okay, so let me get another one. I'm still trying to get. Okay, so let's take this example. Let's take this example. So let's say the summation from 1, okay, to infinity of 1 on n to the power 3 on 2. Okay, so this is a P series. Okay, and for the P series to converge, okay, P has to be greater than 1. Okay, and it diverges if P, okay, is less or equal to 1. Okay, so you can just know this, that okay, for the P series to converge, the P, okay, the P where the P is in this relation, okay, the exponent must be greater than 1. Okay, now remember this falls under the convergence of positive term series. So the first thing we have to do is to show that this is convergent. Sorry, this is positive. So it is decreasing. Okay. 3, what's the last one? It's continuous. Okay. So let's do the decreasing one first. So to show that it's decreasing, okay, we redefine it. F of x is equal to 1 on x to the power 3 on 2. Okay. So this is the same as what? X on negative 3 on 2. So to find a differential, we get what? Negative 3 on 2 x to the power what? Negative 5 on 2. So this leaves us with what? Negative 3 on 2, the root of the fifth root of x. Is this correct? No. We have this rather. Yeah. So we have this. So we saw that f prime of x is this. And since we have a negative here, okay, we can conclude that this series, okay, is decreasing. Now, by observation, okay, no matter the variable we put in here, we always get a positive digit. Okay, and we can just say that this is continuous. Okay, when we do that, we get 5 marks. Okay, now we come and conclude again that from the relation 1 on n to the power p, okay, since p, in this case 3 on 2, right, is greater than 1, okay, then the series is convergent. So since 3 on 2 is greater than 1, okay, this 1 on n to the power 3 on 2, okay, is convergent. Okay, is convergent. Then we conclude. So your conclusion alone, okay, gives you what? 2 marks. Then we are done. So the question alone, so if this was defined on an interval, okay, before we start, you have to say that, okay, where n is greater than 1 or something. So this again is worth what? 1 mark. Then your solution gives you what? 7 marks. Okay. So this is all we have to do for today. Tomorrow we'll have our last section. Okay, we'll have our last section. And for the last session, we'll just be doing the comparison, limit comparison, alternating, and the absolute convergence. Okay. Then that's basically what we will be doing. So thank you all for joining today's section. Let's just pray so that we call it a day. Father, we thank you for today. Thank you for preserving our meeting. So, brother, grant us understanding and you take over preparation, oh Lord. In the name of Jesus, name we pray with thanksgiving. Amen. So, thank you all for joining today's section.
Please, I
If
have a
there is,
yeah, please, I want
hello,
to ask if you can. Yeah, please, can you hear me?
yeah, I can hear you. Yes,
Please, I
please,
want to ask
I can.
if you can list. I want to ask if you can list the things you did for today, so that in case we are like revising, you know what to revise on, like what you've done for this session.
What you've done from this section?
Yeah, from this session, like for this session.
Oh, I can't hear you. Okay. So let's start on WhatsApp. My microphone is very blessed. So okay, so let's chat on
Okay.
WhatsApp. Okay, yeah. So thank you all for joining. Okay, Charlie. See you all the best, all the best. Bye. If there's like any part you don't get, like any concept, kindly like put it in a group or my DM. Okay, yeah, like let's do that and let's please be very aggressive. Okay, so bye. See you all.